Welcome to Growing Worlds, the podcast where we explore the science of exoplanet through conversation with early career researchers on the front line of discovery. I'm Lorenzo.
And I'm Jenny. In each episode, we meet a guest who takes us behind the science of planets, stars, and the search for life in the universe.
Today, we are turning our gaze upward to one of the trickiest components of exoplanet science, clouds. When you hear clouds on other planets, you might think of fluffy white vapor like on Earth, but it can be more exotic than that. On exoplanets, cloud can be silicates, sulfur compounds, or entirely unfamiliar particles, and they play a profound role in what we observe.
To help us understand how scientists model and observe those clouds and why they matter for our understanding of distant worlds, we're joined by Dr Sushuang Ma from King's College London. Sushuang, thanks
Hello.
so much for being here.
Thank you for inviting me.
Sushuang is a researcher at King's College London whose work centers on modeling and retrieving of clouds in exoplanetary atmospheres. She is the lead author of the study Ma, which represents a new modeling framework for clouds microphysics and radiative transit in exoplanet atmospheres. In her research, she explores how to infer cloud composition and size distribution from the observed transmission spectra of exoplanets, and how we must go beyond the simple opaque cloud model if we are to interpret the next generation of observations.
So, Sushang, we always like to begin with your personal journey. So, why don't you tell us what kind of drew you into studying exoplanet atmospheres and how did you get into clouds? Was there a particular moment or was it a slow evolution?
It was both, and it was a long journey. So a lot of people, like a lot of people, I was always fascinated by the extrasolar world in general, but I was never like thinking I can actually do it. So I chose a engineering degree to do, but I was good at it, but I didn't enjoy it. So
Okay, yeah.
whenever, yeah, it was a little bit, I don't know, it was not easy, but meanwhile, it's not challenging in a way that I want to be. So whenever I get time in the break, I just go to the library, right? I find a corner and there are magazines and books of general physics or astrophysics.
Yeah.
Just going to watch, like read them. Of course, I never told any of my lecturers, like I'm going to read
No?
something. No, of course not. They always thought I'm going to pursue engineering or at least a computer science route. Yeah, and one day I just read about this James Webb Telescope launch. But I remembered I read a similar article a while ago when I was a teenager. I read it before. I was like, how could like it launch twice?
Yeah.
Then it, yeah, it
Yeah, that
was.
is not your
Yeah.
fault. I think it's probably on JWST that it takes a while to actually be launched.
Yeah.
I thought I might have dreamed the first time I read the content, right? But then I read
Yeah.
again, okay, it was delayed.
Yeah.
And now we know, like, it's even more delayed. It was actually not launched until I was almost to start my PhD.
Mm.
So I first read it when I was a small kid.
Yeah. Yeah, I think if I recall correctly, the original planned launch date for JWST was 2007 with a $500 million budget, and it was eventually 2021 with a $10 billion budget. So 20 times over budget, 14 years late, but better late than never because now it's fantastic.
I'm
And
pretty sure that when they designed the telescope thinking about the next generation of scientists, they weren't thinking about growing up together with the next generation of scientists from middle school to actual the doctorate.
That's true, yeah.
yeah, but it was a moment because I
Mm.
read the article carefully because I was thinking maybe I had a weird dream and predicted the future or something. And I read the magazine, like, wow, they can actually do this for exoplanets. I feel that magazine was more general. It's not towards exoplanets, especially like, but different topics in astrophysics. I go, okay, I hope one day I can use a telescope, right? And then I got really bored In the meantime, well, I hope no audience is studying engineering or like from
Hey, but look, that's okay because like just because it's not your cup of tea doesn't mean it's not anyone else's cup of tea.
yeah, yeah. Don't get me wrong, engineering is very meaningful, and yeah, if you like it, please keep going. And I start to apply for anything in astrophysics, planetary science for a master degree. But it wasn't easy because it jumped off the major. But somehow I got enrolled into that time was University College London, and I got into this course for planetary science. I was very excited. I was like, okay. It was also COVID. It was yeah, my family
Yeah,
wasn't
true.
supporting it. Definitely not. And I was like, no, I need to go because this is the only chance I can change my major. Then it was difficult because a lot of astrophysics courses, I've never taken them. I only have the knowledge of the basic physics and mathematics. Yeah, so that year was particularly hard.
Yeah,
But
like a really steep learning curve.
yeah, and also it's a self-learning progress. And then I met Giovanna, who's my supervisor. She's a PI of our mission. Lawrence has
Mm.
something to say, yeah.
Yeah, I just want to clarify for the listeners that when Sushang so friendly say Giovanna, she means Professor Giovanna Tinetti, which is the PI of aerospace mission.
Yeah, somehow she just think I'm a very keen person. So she gave me this
Think you are.
opportunity.
You seem
Thank
very
you.
keen on this podcast, so
Yeah, of course. Like I like sharing the story and inspiring the people who are also interested. Because it wasn't straightforward to me to be in this field. Like a lot of things come by luck, but also come by effort.
yes.
I forgot to mention, even when I was in my bachelor, I go to the relative courses. So I finished my major, and meanwhile, I sit in other classes, and I begged the professor, can I take the exams at the same time? So I was doing two majors, but I only get one degree because at that
My
time it wasn't like,
goodness.
it was a
Yeah.
journey. And Joanna later gave me these projects to do, right? And then she think, oh, you did well. How about considering PhD? I like,
Nice. I love that. Yeah, because
mhm.
it was a bit similar for me, like, when I was doing, like, the masters, it was some of my lecturers said to me, like, "Have you thought about doing a PhD?" And I was like, "No." Not because, like, I didn't think I was capable, but just because, like, no one in my family had, done a PhD, and I didn't know anyone who had, like, done a PhD, so it wasn't, like, something on my radar, so I really like it when the lecturers, like, encourage you to take that next step and everything.
Yeah, I think it's fair to say that you find the right mentor can really change your life.
Yeah,
Yeah.
100%.
Absolutely. I feel it's half like the research you do before choosing, half it's really by the opportunity and luck, I'd
Yeah,
say. Yeah.
it's, like, half what you know, half who you know.
Yeah. Yeah.
'Cause you gotta have
Absolutely.
the right people around you, but you've also gotta have, like, that capability. So then you get onto the PhD, and the PhD is all about clouds?
No, it's actually not. So I finished at clouds. Well, the clouds was the starting point because it will ensure I can graduate from PhD. Also, I have started doing it. While in masters, I just refined, especially in the retrieval framework, and tested, published a paper, then put there for some people in the group to use. And then we got the James Webb data public. Like it was after the commissioning, after the first batch of data and initial publications, and I saw this data online. I was like, okay, maybe I can do something now with my cloud model because they didn't contain that into their initial analysis, like a comprehensive way of cloud microphysics. Then I realized it's not only the cloud. So cloud is just a part that needed to be optimized, but it's really about the chemistry, the temperature of the atmosphere, and the cloud together. So I started to refine this methodology. I don't know if we'll have a chance to talk in detail later, but it's about how to find a sweet point between you do the complex physical models using the theories, but meanwhile you have the observation. There are data limitations. There are certain information in the data. How do we go from two direction, meet the sweet point of a best fit of the model to the data. And in that research, I put the 1.09b as a case. And I found like there might be a new explanation of the atmosphere using a new chemistry there. That was quite exciting. It wasn't planned at the beginning of a PhD. To be honest, at that time, I was doing the large-scale simulation. I was doing with the Lorenzo. Can I say it?
Of course you can. Of course.
So we were doing the large-scale simulation, basically populational simulation and retrieval to prepare the aerial mission. And then one day I disappeared. Lorenzo kept asking me, what the hell
And
are
I'm
you
still
doing?
waiting for her to reappear in my radar.
I'm so sorry. That was because I found these new things in this planet and I have to focus like it was just
Mm,
out of plan.
I'm glad that you're mentioning this because this is real life in science. You're just
yeah.
working with somebody on something very exciting, and then that somebody disappear because something more exciting is just coming up, and then
Yeah.
eventually they will be back. I hope, right?
Perfect. I think I disappeared for not 3 years, but almost.
Oh my goodness. Are you going
Yeah,
back soon?
very soon. I will wait for 3 years to reach 3 years and
Yeah.
go back.
On the anniversary.
Yeah,
I'm glad that this is on record now. You can back down now because it's recorded.
Yeah,
I can use this
exactly. It's
against
written.
you.
no way.
Yeah, it's written on the airwaves. So
But focusing on your other work, the one more exciting that brought you away from me, basically, you'd say that you need to find a sweet point between complex models, including the clouds, to understand the chemistry and to get actually understanding of the data that we got from space. So help us understanding this complex thing that you are doing and you are bringing us today. Why don't you start walking us through why clouds are so important in exoplanetary studies and how they are changing our understanding of what we see?
First of all, from the current understanding, of course, we don't know everything about exoplanet because these are distant world. We have limited observational data. It's just a beginning. Many exoplanets we see they have clouds in it. Even before James Webb, we only have very limited data points. People were thinking, they were proposing some of the continuum, or when you see a flex spectrum, these are caused by clouds. That seems to be a most reasonable explanation. And we also see the clouds in the solar system planets. So it should be there. But why we don't have these cloud models before, and I needed to work on it, it was because it was just a couple years ago before James Webb, we only have limited data. For example, Hubble, 1.1 micrometer to 1.7 micrometer. This band, we only see certain absolute features from water or methane or a couple more, but not very direct signatures. And that part, usually the cloud particles, the features are quite featureless. If
okay.
it's like, yeah, for example, if it's 10 to 30 micrometer, will be flat, almost flat, not completely. Maybe you'll see a little bit the scattering slope, but not significantly. So there was no need. There's a word Lorenzo taught me, the information content of the spectrum. I don't know if you created it or not.
Oh, I haven't created that, but thank you for giving me the credits.
It was quite useful. If your data doesn't contain this much information, then you should probably not to put this much complexity in your model and
Yeah.
trying to fit it, because that might be biased by your model. It's
Yeah.
not going to be constrained by your data. But because the cloud, if it's thick, is going to block the signatures from below the cloud deck. If it's semi-transparent, it will block a little bit, so make it more flat, seems to be more flat. In this case, it makes it harder to determine. For the major traces, for example, commonly we see water, carbon dioxide. How abundant are they in the atmosphere? It's difficult because the cloud has attenuated
Yeah.
signals.
Yeah.
And for those minor traces, because their signature wasn't significant at the beginning, even there's no cloud. But if you have cloud, you cannot see them. And to have a comprehensive understanding of the atmosphere, including all the aspects, let's say the chemistry, clouds, temperature, or where it becomes opaque. We do need to understand this component, at least its impact on the spectrum. When we say spectrum, it's the transit depth spectrum. The transit depths we measure when the planet transits in between the observer
Okay.
and the parent star. The atmospheric part of the exoplanet will block, but not entirely, the
Yes.
starlight.
Yeah, so some will like make its way through that atmosphere.
Yeah, and it's wavelength dependent.
Okay, so depending on how that transit dip changes, depending on the wavelength you're looking at, you can then get information about the atmosphere and the clouds.
Yeah, exactly. But usually the cloud part of the signature is not that obvious.
Mm.
But when we have wide coverage of wavelengths, some
Which we have now with like JWST instead of just Hubble.
exactly,
I
and also
see.
the forthcoming Arrow mission where Professor John Dent is a PI.
Yeah.
Yeah, it makes possible with student to optimize, of course, the impact of the cloud on the spectrum, and it helps us to better determine the abundance of the gas phase chemistry.
Okay. Because the makeup of the clouds gives you an insight into that.
It, I would, yeah, I would say it's the necessary part we need to put into fitting the spectrum.
So what sort of clouds can exoplanets have? Because I guess our clouds are water based, right? Mostly,
Yeah.
like pretty much. So are we always looking for water based clouds, or are we looking for clouds of different materials? Is it? I guess that it would depend on like temperature and things like that.
What Jen is asking
Absolutely.
is that if she's looking at the sky while it's lying on a green grass field on an exoplanet, what kind of shapes can she see on the
Yeah,
sky,
yeah.
basically?
That's the real question. Like, am I seeing a horse? Am I I'm joking. No, but seriously, it's like what sort of like cloud content are they all water vapor clouds or are we looking at different types of clouds?
No, different types of clouds, but all in the bear shapes. I'm joking.
Yeah, all
Um,
in pear shapes.
you're correct. It depends on the temperature, but there's another component is what's the baseline, those gases that are going to form the clouds. So imagine you have this amount of water on the earth, and a certain part of it is going to form clouds because it saturates. So it's two major factors. But also the gas phase abundance depends on the temperature and other factors like the elemental ratios and type of chemistry in the atmosphere. But temperature is really a key parameter in determining uh, composition of the clouds. Like in the colder regime, like the Earth temperature or the Jupiter temperature, we have the ammonia and the water clouds.
Okay.
Um, Going further, you might have those chloride or sulfuride clouds. And when you reach like 1,000 to 1,500 Kelvin, now it's in
Yeah.
hot Jupiter
So
region, it's
hot.
quite hot.
Yeah.
We don't have
Yeah.
this planet in our solar system. These are closing planets to their parent stars. Silica clouds dominate. This is our current understanding, but
Yeah.
maybe a month
Like
later,
silicates like rocks are made of silicates. So you've
yeah,
got like
yeah, in
flowing
the sky. Can you imagine?
like, yeah. God, that's wild. I guess this is where, because you see sometimes they're like, "Oh, on this planet, it, like, rains diamonds," and I guess, like, that's the kind of thing that they're on about because it's, like, carbon and it's hot or something, and so, like, it makes diamonds. I guess that's, like so you can get all sorts of crazy clouds.
Yeah, possibly.
Yeah.
If they have the drastic temperature changes, so you may form something really crystallized.
Yeah.
Yeah, the diamond might be possible.
Maybe.
And different colors. Then going further, guess what? You might have iron clouds.
Oh my goodness. Yeah, if it's hot enough.
Yeah,
God, that's wild.
And how are all these different kinds of cloud affecting the actual transmission pattern that we were mentioning before?
their scattering and absorption features are different. So first, the composition will shape a little bit of this overall scattering and absorption features when we see different wavelengths in transit, we mentioned before. And then the specific particle sizes will also change a little bit, where you are going to scatter more light, where you're going to absorb more light.
So are these like changes, they're really sort of subtle, or are there certain ones that kind of pop out?
Certain ones pop out.
Ooh, okay.
Yeah,
And
but
that's why
it's
they're so important to factor into the models and things like that.
mhm, yeah, and it's really case dependent. And
Okay.
yeah,
Okay, so it's like the signals of like different gases in the atmosphere will always be the strongest, but then the clouds have a very unique signature that's smaller, but it's like you can't mistake it. That's a cloud signature.
it's not a, but a continuum, a list of small signatures. Some pop out
Yeah.
a little bit more than others.
Okay, yeah.
That's why we need large wavelength coverage to determine which one is it.
So how do you kind of factor all of this into a model to compare to the data to kind of like analyze what's going on? Like how do you how do you pull all of this together, all of the different effects of all the particles and I just how? I just can't even conceive how you even go about starting to like make models to then interpret the data.
I need to refer to a technique first. It's called the Bayesian technique, retrieval. If you have heard about it, the retrieval studies in the exoplanetary transit spectroscopy, we have the data, we have the model, how to fit them together.
Mm,
So in iterations, we explore a parameter space. So basically this space, I might have this parameter for cloud, this parameter for water, this parameter for methane, and we try different settings. Or when I say
okay.
different sets, it's like 10 to 4 to 10 to 6 sets, this much.
Wow. So tens of thousands,
Yeah,
even hundreds of thousands of options. So it's like one will have, say, 10 parts per million of methane, and then the next one's got like 15 parts per million of methane, and then the next one's like 20. And then you got to start changing the carbon dioxide, and then you got to like change
yeah.
the water. So you got like all these different degrees of freedom, and all of them have to be varied. And wow.
Then we let the computer to decide which sets. Like we won't decide one of these is the best. We decide the region that's more likely to be the ground truth.
Okay. Yeah.
So same for clouds. When we think about it, if you think from a formation perspective, you have the nucleation, you have the growth, including the condensation, calculation. But does the spectrum contain this much information? The answer is no. So we start to think from the observational perspective, so different direction, and see, because we are going to use these Bayesian techniques, or let's call it directly retrieval here. What can we retrieve? So the most direct thing that determine the cloud impact on the spectrum is going to be most likely retrieved. What are they? So the composition of the cloud species and the cloud particle size distribution. So the species, yeah, we can still infer from the temperature and the composition of the atmosphere. But the particle size distribution is really complex.
Mm.
What can we do? So there are studies of simplifying a certain distribution into one radii for a certain layer. So the simplification. Then we can retrieve like which is the radii that can give us this relatively close to the actual signatures of clouds into the transit depth.
So is it like you do sort of lab experiments that will then tell you, well, this range of size of particles is possible, but nothing else is. So it kind of limits your options a little bit and makes it
Or
easier.
kind
Is
of
it like that?
possible compared to the data, let's say.
You mean the lab results of the radial transfer properties, or like in this
The to
condition,
sort
what
of
sizes can it form?
the sizes of the particles.
And this part is from the settling models.
Oh,
So
okay,
what's
so it's
it?
not lab experiments.
Yeah, it's more from the gas kinetics. And observation of the Earth clouds.
Okay. Yeah. So, like, our planet is the laboratory.
Yeah, of course, because it's easier for us to do the in situ observations. I believe there are more data from the solar system planets like
Yeah. Okay.
Venus. Yeah,
Yeah.
but it's more complex because they have very thick cloud and like it's different color layers combined together. I haven't seen the data, but I hope in the
Yeah.
future I can have a look.
So, like, by looking at Earth's atmosphere and the size of the particles, like
Mhm.
in our atmosphere, depending on like the pressure and the temperature, then that goes into the kind of exoplanet models. Is that right?
And we do consider the draft balance. So it's a balance between the upward turbulent mixing and downward sedimentation. And with that draft balance, give the properties of the atmosphere. So you think about a particle that's like traveling into this viscous flow, and either it grows or it just drop down,
Yeah.
or it just
Okay.
suspend. Like yeah,
Yeah.
yes. And this approach is originally from Marty. They have proposed a model. For me, it's more like from a numerical perspective to make it more accurate, and then how to combine it, connect to the radial transfer, and combine it into this 10 to 4 to 10 to 6 times iteration.
Yeah. Okay. Yeah. And so then once you've got your sort of the area of parameters that fit, then that gives you your idea about what the temperature and the pressures like in these clouds, what they're made of, like what the size of the particles are. We plus or minus a bit, right?
Yeah, I need to mention everything is down together with the chemistry, like the gas phase abundances, because you cannot ignore those signals. And
Yeah.
also, the baseline gas abundance really indicate a little bit how much these clouds are going to form.
Yeah.
Okay.
Yeah.
So you say, though, that it's quite difficult to get all these details, and there is a balance between what you can model and what you can actually detect, right? You mentioned before that fitting the data, mostly depends on the data. And moving from Hubble Space Telescope to JWST, we have larger data set, larger wavelength range, we can do more. So now that we are moving to the area that, as you mentioned, about JWST and aerial and possibly beyond, what you think will be the best improvement that we're going to have? Improvement in instrumentation or in modeling? What's going to be the difference in the future? What we're going to learn more compared to what we know now?
You mean from the modeling side or from data side?
I am in from data side because I'm a technical guy, but I'm happy to listen also
Okay,
what you
I'll
see
be
on
a
the model
friend.
side.
So some data said but in simulations I tried to decrease or let's say increase the SNR because a simulation can do that. When you increase the SNR, you can really like constrain more things like the even the eddy diffusion, like to have
Wait a sec.
more.
When you say increase, sorry if I'm interrupting. When you say
Yeah,
increase in SNR, you mean that
yeah,
the
topic
signal is
mentioned.
easier to detect compared to what is actually our uncertainty on the measurement?
Of course, SNR is signal to noise ratio. Yeah, so signal is more clear. You're absolutely correct. So it gets much easier. Basically, the information content you taught me is going to increase a lot. So you can constrain much more precisely the atmospheric processes that's related to cloud formation. In that case, people can think about even more detailed analysis on the cloud particle size distribution. And remember, the clouds are not composed of single type like chemical compounds. It's actually a mix, but we were not able to do it at the moment. But I'm saying when I increase SNR, I increase it to much higher than the capability of James Webb and Ariel, unfortunately.
Yeah.
So realistically, what can this instrument do now is to limit the effect of clouds in determining the gas phase chemistry processes. We might propose different scenarios at the same time because there are some uncertainties of different type of clouds and their particle distributions. And
Mm,
even in the radiative transfer, even you have the particle distribution and composition correct in simulating its impact on the spectrum, you have this laboratory data that's not very certain.
yeah.
Yeah.
So would you say is the biggest kind of challenge now for trying to infer all of these cloud properties? Is it the models that are limited, or is it that signal to noise ratio in the data?
Can I say it's a signal to noise ratio of the
You can
data?
you can say that.
And
That's absolutely
yeah,
fine. I'm
yeah.
here to mediate between the modeler and the data analysis. Yeah.
It's always our fault.
So do you think like the modelers have kind of got a pretty good handle on the atmospheric science, but now we need that more sensitive data, which we're starting to get with JWST, but it's really about waiting for those future generation of telescopes like Ariel.
You know what? Because our model are based on the Earth data, like if we increase a little bit the boundaries, is to the solar system data. But exoplanets are different. Our solar system is quite unique. If we
Yeah,
don't have data, we cannot refine our model. It's like the chicken and egg, right? But
it
in this case,
is. Yeah.
I really think the way to push it is the data. And not only the exoplanet data, also the aerosol data, like when I say it is the refractive properties of these cloud particles from laboratories. But one thing
Okay,
is
yeah.
difficult is how can we like make these, for example, silica clouds on the Earth in the laboratory? It's a very
Yeah.
high temperature.
Yeah, it's quite difficult. So yeah,
Yeah.
so I think it's a little bit of column A and a little bit of column B in the sense of we need more sensitive data, more, higher resolution data from the telescopes, but the models need to also have some work with more feeding from the lab experiments and more detailed studies of atmospherics to kind of feed into them. So look at me keeping a happy medium between the two of you.
Thank you, Jenny. You're so diplomatic.
Yeah, I
Thank
try
you.
to be. I try to be.
So we will be in much better mood, like when the 3 year hits, when we start the collaboration
The
again.
aerial stuff. Yeah.
Yes.
So I think before we wrap up, we always need to finish on our signature question. And our signature question is this one. So if you had to pick one celestial body, star, planet, cloud layer, something else entirely that reflects your work or how you think about it, what would it be and why?
For sure, it will be an exoplanet with clouds.
Yeah.
I think I'm someone who like the big pictures. I always think from the big pictures, then go into deeper questions, like specifically one point I'm interested in and I think it in a complex way. But I'll start with big pictures. So it will be something like bigger, like the hot Jupiters.
Yes.
I'd say like the one I'm actually studying was B39 is a good example. So it has the cloud layers, right? So you do go deep and think what's beneath there.
Yeah.
Yeah, I'll pick this one.
Nice. I like that.
That's a really nice one. Thank you, Sushang. Thank you for lifting the veil of clouds, showing us what hides in the sky of other worlds that often hold the key to understand them.
And thank you to everyone listening. Join us next time on Growing Worlds as we explore another corner of the universe and the people bringing it into focus. Thanks for sticking around, Shushan. It's been brilliant.